Hello and welcome once again for another example problem. So this is day 3, example problem 2 for ES 340. A body whose surface area is 0.5 meters squared and temperature is 150 degrees Celsius is placed in a large evacuated chamber whose walls are 25 degrees Celsius. What is the rate at which radiation is emitted by the surface in watts? And what is the net rate at which radiation is exchanged between the surface and the chamber walls? Okay, so for part A, recall that we had this equation for the rate of radiation, which is Q dot is equal to to epsilon times sigma times A times T to the fourth TB to the fourth power. Okay, so we had this equation, and that's for the amount of radiation from a black body. This is the Stefan Boltzmann law. So if we have this, then our rate of radiation then of course becomes this. And what we need, though, when we're dealing, and this is true in general, unless you have a difference in temperature, in which case the difference of two things in degrees Celsius is the same as the difference of two things in degrees Kelvin, because the size of the degree in each of those cases is the same. So if there's a difference, you don't have to worry about it. Direct difference, not like a difference of squares or something like that. But if there's a difference like T2 minus T1, then you're safe. But otherwise, you should always convert to absolute temperature. So that's what we'll do here. We'll convert to absolute temperature. And the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. Now your book often will round that to 273, so just be aware of that often it's just rounded to 270, adding 273. But in any case, we get epsilon, which was 0.8, I think I forgot to write that in this problem. But epsilon was 0.8. Now sigma is given by, this is the Stefan Boltzmann constant. And in SI units, which obviously we're using because we have degrees Celsius, meters squared, all that good stuff, this is 5.67 times 10 to the negative 8th watts per meter squared times Kelvin to the fourth. Okay? So we can epsilon has no units, by the way. It's a unitless quantity. So times 5.67 times 10 to the negative 8th watts per meter squared times Kelvin to the fourth. The area, well, the surface area was given as 0.5 meters squared. And notice this is in square meters, so we don't have to do any conversion. That's convenient there. So 0.5 meters squared. And the temperature now, that's the only thing we have to actually do this conversion. So our temperature, 150 of our body, is going to be 150 plus 273.15 Kelvin. So that's going to be equal to 423.15 Kelvin. So I have to multiply here by 423.15 Kelvin, all taken to the fourth power. Okay, and notice that the units are going to work out nicely here. So our solution, if you multiply this whole thing out, our solution becomes about 727.14-ish watts. Okay, and then part B is similar, but now it asked what is the net rate at which radiation is exchanged between the surface and the chamber walls. So in this case, if you remember from previously when we were discussing this, we do have an equation, but we have to make an assumption which is taken care of here, placed in a large evacuated chamber. So if the surrounding system is much larger than the body, then we can make this approximation, which is that QE dot is equal to epsilon times sigma times A, now times TB to the fourth minus TS, where TB is the body temperature again, and TS is the body is the temperature of the surroundings, which in this case ends up being the chamber, the evacuated chamber. So since we have that, we can actually just substitute in all these numbers now. But we do need to convert the temperature of the chamber walls into Kelvin. So TS is going to be equal to 298.15 Kelvin. Now, notice that this is not the difference between two temperatures. It's the difference between two temperatures where each individual one is taken to the fourth power. Because of that, we cannot do what I had suggested before, which is if there's a difference. So if it had been TB minus TS, then we would be able to just take the Celsius temperatures and be fine. But in this case, they're taken to a power first and then subtracted, and that's not the same as having say TB minus TS all to the fourth power. That would give a different expression. So we can't do that here, and so we will just use the absolute temperatures. Minus 298.15 to the fourth Kelvin to the fourth. And this ends up working out, if you substitute in all those numbers, this ends up working out to being a 547.9, approximately 547.9 watts. Okay, that's it for this video. Hope to see you again soon.